Thank you everyone for joining this talk. It's called Schema-First Telemetry, and it's based on the paper we published in SIGOPS in the summer. I will have a link on the last slide. My name is Yuri Shkuro. I'm a software engineer at Meta. I work on observability platforms and observability products. I also am active in open source. I'm a maintainer of the Jaeger project, and I've been serving on governance and technical committees in the OpenTelemetry project since its inception. I also published a book on distributed tracing a couple years ago. For the agenda of this talk, I will first talk a bit about the terminology so that we are all on the same page when I say metadata and other words. I will introduce the schema-first approach and talk about specifically the implementation of this approach that we are building on in Meta. And I'll also do a comparison of the other approaches that exist in metadata in the industry today, and hopefully we'll have some time for Q&A. So, first of all, the first term we need to kind of bring up is the observability, which is the ability of us to understand the internal state of the system by looking at the outputs or signals from that system. And when we say outputs, we're primarily talking about telemetry that we collect from the system, not so much the actual responses that it produces, although that could also be part of the observability. And to get that, we need SDKs to be running or some agents to instrument the application so that we can get telemetry out into our observability platforms. And there are many different types of telemetry. I will specifically be talking about the 6 telemetry types: metrics, events, traces, logs, profilers, and exceptions. There's no particular order in the significance there, just a nice acronym that I came up with. And there's a blog post that I talk about why I think these telemetry types are important for cloud-native applications and why I consider them different types. All these telemetry types have one thing in common. They describe the behaviors of observable entities. And when we say entities, those could be some infrastructure components like hosts or rack or service instance, or they could also be instances of some business-specific workflows or user activities or customer count. And so the way that telemetry identifies those observable entities is usually by capturing dimensions alongside the telemetry itself. So here we have an example from the open metrics format where we have a metric called request latency with 2 dimensions, service and endpoint, and the value. And to be specific, dimensions are not metadata, they are part of the data itself. The one problem with dimensions is that by themselves, they are not sufficient to understand the telemetry properly. So consider these 2 metrics. We can easily spot a number of issues in them. First of all, they seem to represent the same concept, but they're named differently. They seem to refer to the same value, 15.2 milliseconds, but the value is encoded in different units. They have the same service dimension, but the values are clearly represented using different domains of values, and same story with the endpoint. So that situation is probably all too familiar to anyone who worked in a large organization where you have hundreds of services written on different frameworks and different languages. And so enforce standardization across your whole organization to make sure that through the naming and other things, your things that you describe in the telemetry are the same. It's a pretty difficult task. And so this is where we come to the metadata. Metadata is really the additional data about the telemetry, which can allow us to reason about what those values in telemetry are. And metadata can encode many different types, like from simple things like data type or units of measure or description, to more complex types like what's the ownership of this particular telemetry asset, or what are the semantic meaning of specific dimensions, or even the asset itself, and even going even more complex, what are the purpose policies for specific data elements, who can access them or not. And when we have this kind of capabilities in the system, we open up a lot of possibilities to build much smarter telemetry platforms. So users of telemetry often complain that it's difficult to discover or make sense of all telemetry coming from the system. So when we have a metadata space, we can query into that space and answer questions like, show me all telemetry artifacts for my service or for services owned to my team. When we explore in the data, tools can use metadata to assist with query building, like suggesting suitable values and operations, and which dimensions can be suitable for grouping and aggregations. Cross-filtering and correlation is the process of applying certain filters across many telemetry artifacts at once. So imagine we have a dashboard which shows multiple metrics from a system. When that dashboard understands the metadata of this telemetry, it can automatically recognize that, for example, all these signals have a data center as a common dimension, then automatically put it up as a filter on the page. If you don't have metadata, the only way you could do it is by sort of like semantic conventions that your data center is a dimension in the fields. Metadata can also describe constraints on the telemetry, and those constraints can be either validated at runtime or sometimes even enforced through code generation at compile time. And compile time dependencies on the schema allows us auto-discovery of dependencies, which makes sense. Like if you want to make changes, you don't want to break your consumers of this data. And finally, purpose policies allow to encode as metadata to restrict access to the data or for various purposes like privacy control or other security reasons. So now I will talk briefly about what are the existing techniques in the industry. And obviously, when we say metadata, we're talking about some machine-readable format of the metadata so that the telemetry platforms can understand it. So in OpenTelemetry project and in other projects like Elastic Common Schema, there's a broad group of conventions for telemetry data, and conventions are ultimately guidelines about how you name dimensions of your telemetry. So, for example, if you want to refer to a source IP, that would be a specific format of that dimension, like source.ip in ECS. And those conventions exist for various domains of the operations, like RPC conventions, HTTP database, etc. The other type is existing in OpenTelemetry as well as telemetry schemas. They are attempt to provide versioning over semantic conventions. So this is not like a completely new methodology, but at least schemas solve some of the problems with the metadata. They allow to define transformations of attributes and so like help with the versioning on the spec. The third technique widely used is metadata, which is just created after the fact. So you write your metrics or your other telemetry, and then you have a metadata store where you can go and annotate those artifacts with some metadata essentially, and then your tools can query that stuff. And finally, a very popular technique with many commercial vendors is to automatically enrich telemetry with some infrastructure-specific dimensions, like in which Kubernetes pod your service is running, what host name, and other things. So that technique is pretty good in terms of providing consistency across telemetry, but because it's automatic, it's only limited to some specific infrastructure dimensions. It's not generally extensible to any arbitrary telemetry. And that brings us to the main topic. So while metadata is a broad category, and the benefits that we discussed, they all come from the schema of telemetry. And when I say schema, I use it in a broader sense than just the shape of the data, because in schemas, we can encode other information like semantic types, ownership, etc. We probably remember in the early 2000s, there was a lot of buzz about NoSQL and no schema data stores, which had a lot of benefits for simplifying storage requirements. The value is just a blob. But it was not a particularly good way to build applications, because if I'm writing business logic, I would rather have to know exact shape of the data that I'm working with and its schema. And I prefer that even to be strongly typed and checked at compile time. And so this paradigm of schema-first approach has taken a very strong hold in the RPC space these days. Usually, when you start a service development, you start with defining your API in some sort of interface definition language like protobuf. This is what's known as schema-first approach. And at Meta, most of the warehouse datasets are already produced in this manner, but not so much in the telemetry, application telemetry space. So this is our attempt to solve that problem as well. Before I jump into that, let me just take a quick look at another technique which is actually prevalent today, and it's a code-first telemetry. In that approach, the shape of the telemetry is fully defined by the code that emits it. So here we have a counter with 3 dimensions. The dimensions are passed as a dictionary, free form, and the code is the source of truth of the shape of this metric. If we want to add a new field, we just add a new key value to dimensions to the dictionary, and we could easily break our consumers by doing that, because really there's no controls in this methodology whatsoever. So in the schema-first telemetry, in contrast, we start with a schema of the shape of this data. So we define in some interface definition languages struct, saying these are the 3 fields in our telemetry asset, and then when we run it through the compiler, it generates a struct called request counter in this case, and then when we need to emit the telemetry, we populate that struct with values and pass it to the SDK. So there are 2 things we can see here immediately. Unlike the open-ended dictionary, the struct will not let us make a typo in a field name, as simple as this. And it already provides better consistency guarantees. And also, passing a struct is actually usually more efficient, which is important for telemetry because we emit so much of it. We kind of need to squeeze as much efficiency. Since we no longer pass the key names as a dictionary in every telemetry event, the binary representation is much more compact here. If we want to add another dimension like a shard ID, so first we add it to the schema, and then we add the value when we emit the telemetry. Know that both the schema change and the code change can be done in a single pull request. This was one of the critical design goals for us, because otherwise the change process would have been too complex and we would have had a hard time convincing engineers to use the new model, where compared to the old code first approach where you just add 1 line. So now let's talk about specific implementation details of this approach. First of all, let's step back and look at the overall authoring process. So I described already the top 3 steps, which is define a schema, compile the schema, and change the emission code. Once that PR goes through the CI pipeline, we have another service running called schema actualization service, which is consulted by the CI pipeline to validate that the schema change in this pull request is actually backwards compatible. If it's not, it will fail the CI and not let it through. And when the pull request is being merged, the same service will apply the schema changes safely to the and push it into the metadata store to make it available to the consumers. So at runtime, the metadata store is consumed by tools like UI or telemetry backends. We can see on the right side that SDK is able to emit telemetry in a binary format. This is very different from the most existing open source SDKs today, where dimensions are always sent as key value pairs. And in this example, we emit telemetry through a scribe, which is a queue at Meta, and it goes to the telemetry backend, and backend uses the schema from the metadata store to decode the binary payload. Now, a bit of a step back more, why Thrift I already mentioned. So Thrift is Meta's de facto schema definition or interface definition language. It's similar to protobuf, and it's used to define interfaces between services, or it can also be used to define schemas for these purposes. So most engineers at Meta are already familiar with that and use it on a daily basis. That toolset has a very strong IDE support for authoring, code generation, and automatic cross-repository syncing when you author services in different repositories. And so code generation and serialization are also well supported in most languages to use in the company. The IDL of Thrift is very language neutral and very expressive. To some degree, it's even more powerful than protobuf because it supports type aliases and annotations, which are critical for each metadata needs that I'll discuss later. And finally, Thrift supports namespaces and compositions, which is important when we want to reuse data types and semantic annotations, as well as when we want to have multiple teams collaborate on authoring large data sets or large telemetry assets. So let's look at some examples of adding metadata to the schema beyond just the data shape. So this example shows how to approximate OpenTelemetry Semantic Convention for host resources. We start with a struct definition for the dimensions, and then we add 2 annotations to each field, displaying name and description. So By doing that, we essentially just did what OpenTelemetry Semantic Conventions do, but we did it in a machine-readable and like more reliable way. And then because these annotations sort of like live along with the telemetry, they can be automatically used by the telemetry platforms and tools to like display fields or auto-suggest search in the Power Search bar. Let's look at another example. So how we can provide metadata again in the schema. So in the previous example, we saw that the fields were defined using primitive types like string, int. In an interface definition language, we can define type aliases and use those as a field types. So there are two important reasons to do that. So first of all, in the previous example, we had to add annotations directly to the struct. And that means that if you use the same field in another struct, you kind of have to redo that. With type aliases, you can add annotation on the type alias itself. And that will apply across the board, across all telemetry as it's using that type. And we also, alias gives us actual strong type so that we can have compile time safety with that if we want. And we also can add another semantic annotations to that type to help tools understand what the meaning of this data is. And here is an example of that approach. So we define in two type aliases, hostname and hostname with fully qualified domain name. And then we can use them in the telemetry types, and we add the display name annotations to them so that it's kind of propagates across all telemetry types. We have also another opportunity here. Both types logically represent the same observable entities, just expressed in a different format of the value. We probably can even translate between those values. So we can capture that in additional metadata. So we introduce a new annotation type called semantic type, which takes an argument drawn from a large curated hierarchy of semantic types. And we tag both of these type aliases as representing a data center underscore host semantic type. And we can imagine doing this using other annotations to extend this concept even further. For example, we can add a regex pattern that can be used to validate the value. Because we populate dimensions via code generation struct, we can enforce validation at runtime and even compile time. We can also specify a transformation that describes how to convert one type of values to another. This final example shows how we can apply annotations on the annotations. So here we have a struct with dimensions that describe RPC telemetry, the subset of it. It contains two fields, the source service and the target service IDs. As we can see, they have the same type, which is drawn from the domain of all service IDs. However, the meaning of the field is different, and we want to reflect it in the schema. So what we do is we introduce another annotation called a one-way message exchange actor. That represents the sender or receiver of the message. And we define a corresponding enum to capture the values. Now, in Thrift, the annotations themselves are defined as struct, so they only become annotations when we use the add symbol on them. And the other thing we do is we add another annotation called semantic qualifier to this struct, which will become an annotation in the future. And so what that does is it allows the tools to understand that this particular descriptor is attached to a type. It gives us a unique semantic meaning, so that if you have two different descriptors, then the tools will understand that the two fields are not equivalent, and vice versa. And now let's put it in RPC struct. So we just add these annotations to the fields and tag them as source and target fields. And again, this annotation is reusable across multiple telemetry types. Now, if we build a dashboard with two metrics, which are both annotated in this manner, our dashboard tool can recognize that the source field and that the source service fields are comparable with each other, whereas the targets and source are not comparable, right? And even though, okay. Now, let's compare this schema-first approach with other existing telemetry approaches. So we considered several categories of requirements for doing this, for comparing the solutions. So one of them is how many lines of code we need to do to emit a new telemetry. Another one is how difficult it is to deploy a change. Like, do we need to do something like alter table equivalent in the production? Can multiple teams author the telemetry? If we log telemetry in the different places, will the code and schema be consistent? The second category is change management. Is it safe to do the changes? can we identify our consumers and make sure we don't break them? Do we have compile time safety? Can we apply auto-generated code modification, etc.? And finally, on the consumption side, it's basically all of the benefits that metadata I described previously. Do we have introspection? Do we have semantic cross-filtering and correlations? And now, this is a very busy slide, but I think the point here is what I want to highlight is that if we look at most of these techniques, they do pretty well in the authoring section, but not so much in the consistency section. And then in the change management, they pretty much do very poorly across the board. The only existing methodology which does kind of well is the automatic metadata enrichment that I mentioned with the commercial tools. However, because it does not apply to all of the telemetry, all of the dimensions like custom telemetry, it basically fails in some of the areas. And then our approach kind of gets green marks almost everywhere except for the initial authoring experience because it is slightly more complicated to author. But we feel like for meta with our existing methodologies, it's valuable. And so in the conclusion, why schema-first telemetry is makes sense at meta. They're mainly because it is already a paved path for the engineers. We have the process, we have the tooling built for that, and so engineers are familiar. So we're fairly certain we can make it work for telemetry metadata as well. And it also allows us to do incremental migration. There is no big bang approach here. We can start with a posteriori metadata solution by annotating like very popular telemetry datasets while migrating them to the new SDK. And there is some future work that we also need to pay attention to, like we don't do good story with the versioning yet, as that's sort of like a typical problem for anyone working with the database schemas. And we work on the data governance of trying to define basically who can define semantic types, how we reuse them across the board. And in the interest of time, I'll skip this last slide and I'll just go to the Q&A. So this is the paper that I mentioned, which is on this, the talk is based on this paper, and there's a link at the bottom. So thank you very much. I hope you enjoyed this, and I'm happy to answer any questions if we have time.